Before we do that, let me understand your impression about gravity techniques. You feel comfortable, everyone? Or there are doubts? There are things which are not clear? Anyone having any difficulties around uh, the gravity techniques? Anything that you want to raise, discuss? Let me see. Just give 1 minute before we start. During that time, we can discuss. Okay. Rahul, are you comfortable with gravity techniques now? Is everything
Yes, sir.
okay for you? Okay. Yeah. So are you also, I mean, let me hear it from Krishna Yadav. Are you there? Okay,
Yes,
Krishna.
sir. Yes, sir. It's clear.
Okay, it's clear. And you are okay to read the book of Lowry? Is it clear? I think the book is fairly clearly. So, are you finding it? Are you comfortable reading the book as well?
Yes, sir.
Okay, excellent. Very good. So, I was little. I mean, I there was a comment which we also talked in the WhatsApp about a doubt solving class. Well, I also agree with the majority of the class. I mean, you can always ask me questions, no problem. Okay, you can stop me anytime or write to me in WhatsApp or in email, and we can solve it that way. Uh, unless there is a pressing need of a doubt solving class, then let me know. In that case, we can always have some dedicated time, maybe half of the class for doubt solving if you have doubts. But my preferred model is, as we go along with the with the class, let's keep on solving whatever doubts that you have. I mean, it's not a good idea to keep on piling your doubts till the end of the chapter. Okay, it's better that you get it solved. It's your responsibility that you understand everything. So it's better that you get it solved, along with the class. So let us then start the new chapter that we talked about. Okay, and we are going to discuss about magnetism, start discussing about magnetism, and of course, magnetic methods, right? So, as you know, gravity is one of the fundamental forces that acts in nature. So, magnetism is also another fundamental force, right? This is another fundamental force, very different from gravity. This is one of the fundamental forces that acts in nature. Now, and I mean, we have been from childhood. We know about magnets. That if we take something like an iron very close to a magnet, it actually attracts. If we take opposite poles close to each other, I mean, if we take two opposite poles in front of each other, they actually attract as well. If the poles are same, then they repel from each other. And these things we have been seeing from our childhood, I guess. So we are pretty much exposed to the uh, fact of magnetism. And this was really, I mean, when I was a kid, magnets really did fascinate me a lot. I mean, that was because we were, as a child, it was very difficult for one to understand what is happening. There is nothing going on, but then uh, a material is attracting others. So yeah, it's something that can generate curiosity to any young mind. Okay. Now, uh, this is a fundamental force, and there are some governing equations around it. Now, there is a trouble with magnetism. What is that trouble? The trouble is, I mean, we have derived a lot of, and we will see some of the formulas, some of the equations around magnetism, define its properties. But you know, why essentially magnetism happens, and that is fairly complicated, and it has some quantum mechanical explanation. Not everything is very well explained even in quantum mechanics, the very fundamentals of magnetism. And of course, uh, things are fairly complicated from a physics point of view, from quantum mechanics point of view. If you get into the root of magnetism, okay, so there is a quite uh, large amount of quantum mechanical explanations around it. Okay, so there is a large amount of quantum mechanics involved in understanding the fundamentals of magnetism. But we are not going to essentially look into them simply because we are geophysicists. Let the theoretical physicists be bothered about understanding the absolute basics of magnetism. But what we will deal with, we will essentially deal with those properties and how we can use them. So as geophysicists in geophysics, what we are going to do essentially is to look into the properties in a simpler way. Okay, and that simpler way that we are going to discuss, and you will see why I'm saying it's a simpler way. They might not be always 100% right. Okay, so the analogies that we will invoke to explain magnetism, yeah, they might not be 100% right from a physics point of view. Okay, but the explanation works, hence we are going to use them. Okay? And that's how in geophysics magnetism is actually approached. Okay? So in a very simpler way. Although we are going to look into the same phenomena, you could have looked at it from a quantum mechanical point of view, which is perhaps more right. But then we are going to look at it in a fairly simpler way. uh, using the continuum mechanics principles. Okay, so using continuum mechanics, continuum, made a mistake, mechanics. That is what we're going to do. And of course, we are going to look at its application. That is where our primary aim will be. Look at the application of the magnetic field of the Earth. Look at the application of the magnetic field of the Earth in basically two branches. Okay, application of the magnetic field of the Earth in two aspects. One is, of course, for mineral exploration, like we have been using it for gravity exploration. So that is very direct, it has economic impacts. And the second one is from a paleomagnetism point of view. And this discussion is more, maybe you can say, academic. Okay. By means, what do I mean by looking at paleomagnetism? Like we have been discussing about the magnetic reversal, and then how you can, prove seafloor spreading. We're going to look at in details about calculation of paleolatitudes, how it can be, used in understanding the in understanding uh, the plate tectonics, continental drift, so on and so forth. So that is what we are going to look at in greater details. That is our academic discussion on the application of magnetism, and then of course there is another component of mineral exploration. Okay, like we have been doing for gravity techniques. Okay, so that is more or less the context and our approach by which we are going to look at magnetism. Okay, and so let's start. So, like gravity, before we get into the application, we are going to discuss some of the first 2 3 classes. We are going to discuss some of the very well-known formulas and derivations and equations, some relations, just to refresh. Okay, I'm sure you all know about them, but just so that we are all in the same page. Okay, shall we do that? Let's do that. Okay. So this is let's the easiest representation of a magnet is a bar magnet which has 2 poles, and we call them as north pole and south pole. Okay, and then we draw some magnetic lines around them. You know about these things. I'm not going to spend a lot of time around it, but and then of course something like this, isn't it? I should have started the diagram a little bit lower so that I could have drawn the other side of it. And then we have some vectors associated with the magnetic lines. And then you remember how did we, in your school project, I'm sure you all have done, you had taken a bar magnet, yeah, and then you would have placed your magnetic needles, yeah, at different different parts, closer and away from your bar magnet, and then you could actually join those points to define your magnetic lines. Now this is how the magnetic field looks like around that bar magnet, and any magnet of course will have a north pole and a south. Now if I compare a magnetic field with gravitational field, you remember that this is perhaps Earth's gravitational field. If we look at the equipotential surfaces were like this, and it was directed towards the center of the earth. So one of the fundamental difference between magnetism uh, and uh, uh, and the gravitational field is magnetic field is not central, right? Is not centrally directed. Magnetic field is not centrally directed, but gravitational field is. So the direction varies with azimuth, as you can see. If of course the direction will change from this point, from point P to point Q, depending on where on the magnetic line it is. Okay. Now, what happens if I break this magnet? Remove the gravity. So what happens if I break the magnet? Say, suppose I break it here. I'll create two bars out of it. And then each of them will act as two individual magnets, right? North pole, south pole, north pole, south pole. And then if I break it further, there will be, from each there will be another magnet, and they will have their corresponding north poles and south poles. If we break it further, there will be another few more magnets. Okay, all of them will have their individual north pole and south pole. So if I keep on breaking them, I will create magnets, but all of them will have their north poles and south poles. So I cannot essentially reach to a position where I simply create a magnet which only has one pole, or what we call as magnetic monopole. So magnetic monopole doesn't exist in nature, doesn't exist. Okay? So there are a lot of research going on. I'm sure you know about them, who keep a track about research on magnetic field. That people have a lot of research going on about creating magnetic monopoles. If you can create a magnetic monopole, I'm sure you will get a Nobel Prize. So magnetic monopoles do not exist in. But the irony is, we are going to use the concept of magnetic monopole a lot. Okay, use the concept of magnetic monopole to define the magnetic field. It's like a hypothetical magnetic monopole. And that is essentially done to keep things simpler, to avoid the complicated quantum mechanical explanation and equations. We can use the concept of magnetic monopole to actually explain and derive a lot of fundamental equations related to magnetism, avoiding the quantum mechanical complications by invoking the concept of magnetic monopole, although it does not exist in nature. Okay, now let us say, so now let us say there are two magnetic monopoles, P1 and P2, theoretically, which is separated by a distance r. Then the either the force of attraction or the force of repulsion, depends whether they are the same monopoles or they are different monopoles. Fr, the force acting between them, can be defined as K P1 by R square. P1 and P2 being their whole strength. When this equation was actually invoked, K was thought to be dimensionless. Right. So with that, if I essentially think that this is dimensionless, and for our more convenience, if we think that this is unit, the value of K is unit. If this is That's what our assumptions are. Then we can say that the so force is the unit of force is dyne in CGS unit, right? So P1, P2, or we can simply write down, let's say we call them as P square. Let's call that as P square. And this is centimeter square. Okay. So the unit of P pole strength will then be dyne centimeter, right? So that is the unit of pole strength. Now, if we think that well, let's say I have this is one monopole P1, and let us say this P2 is actually unit. It is, so rather than having P2, this is an unit pole. Okay. So if I calculate the force on the unit pole due to this pole P1, we can actually define the magnetic field around because of the presence of this pole P1, right? So in that case, we can let us call that as the magnetic field due to or we can, because there is only one, we can just say P, a magnetic field due to P is, let us call it as B R, because it will be a function of R, of course, equals to A by, right? Now, in CGS unit, we said K is unitless. So is how people thought, at least. And then P has a unit of root over dyne centimeter, and this is centimeter square, right? Square. So that means the unit of magnetic field will be root over dyne. I mean dyne to the power -1 centimeter to the power minus. And this is what we call. What do we call dyne to the power -1 centimeter to the power -1, guys? Can someone tell me? Anyone? Don't look into the internet from your mind, from your memory. Srivats, tell me, what is this unit called normally, conventionally? Yeah, sorry, that is what oh, sorry, my apologies. Yeah, dyne to the power half. That's right. I'm sorry. Yeah, dyne to the power half centimeter to the power -1. What is this called? CGS units. Yeah, CGS units I know, but what is the common name for this? There is a common name for this. So this is called Gauss, okay? That's the unit of magnetic field. And then there is another smaller unit of magnetic field, which is gamma. and that is equals to 10 to the power minus 5 Gauss. Right. Now later, what people have found that in SI unit, I mean, this is more advanced understanding of scientists, SI unit of K. So in SI unit, K can be expressed as equals to mu 0 by 4 pi, and mu 0 is called permeability constant. That's essentially the magnetism of vacuum. It's called permeability constant, and that has a value of 4 pi into 10 to the power minus 7 Newton. But A is ampere, okay, and this is often called Henry per meter. Okay, so these are some of the units that we need to remember for magnetic field. Now, the next thing that we have to define, like we had defined for gravity, gravitational potential. Similarly, we need to also define magnetic potential. Yeah, and magnetic potential, you know, let us call it as W. At a distance r from a pole of strength P, so suppose I have a pole of strength P at a distance r from it. Okay, if we define it exactly the same way like we had done it for gravity. Okay, so the magnetic field of the pole, so you know, it will be the work done, right? It will be the work done to actually take an unit pole at for a distance r. Okay, so we can define W is equals to, infinity. D is the magnetic field, dr, and then we can further simplify that as mu 0 by 4 pi r. Okay. So that is essentially the magnetic field for an unit pole, okay, for a monopole. Now, of course, we cannot stop at a monopole because that doesn't exist in nature. We have to have the concept of at least a dipole. Dipole is the simplest magnet possible in nature. Now, how do we define dipole? Let's say, let me just drink some water first. I'll draw the picture first and then I'll explain what I'm drawing, okay? Just hang on for a moment. Huh? Let me just draw it first, then I'll explain. Okay. So, say for example, there are two equal and opposite poles. You can consider them as north and south pole. Okay. P plus and P minus. Okay. Located at a distance D. Okay. So the distance between P and P minus, P plus and P minus is at a distance D. Okay. So the potential W at a distance R from the midpoint. So this point, say I call it as, say, X. Okay. X is the midpoint between P plus and P minus. So, and then I want to calculate the uh, uh, I want to calculate the potential. Okay. I want to calculate the potential at a distance R from the midpoint. Okay, at any single point. So there are few more things. Uh, this angle. So uh, this angle is theta, and this angle is theta dashed. So I mean, theta and theta dashed can be anything, depending on where the point P is. Okay, and then this distance is R. Let us say this distance is, we call it as R plus, and this distance we call as R minus. So the work done, W, is equals to mu 0 P 4 pi, can be given as 1 by R plus minus R minus, you know. So so there is one for the positive. So this is this part is mu 0 P 4 pi by R plus is for positive pole, and mu 0 P 4 pi by R minus is for the negative pole. And as they are oppositely directed, of course, they will be subtracted. Now, if I simplify that, I can write down is equals to mu 0 P 4 pi R plus R minus R minus minus R plus. Right? Now, we will define it to be a dipole. So we will call it a dipole only when, you know, D is much smaller than R. Okay? And if we have that assumption in place, we can write down R plus is very close to R minus by 2 cos theta, and R minus is very close to R plus P by 2 cos theta dash. And also when D is very, very less than R, we can also write down theta is very close to theta dashed. Okay. So this term R minus minus R plus, that becomes very close to D by 2 cos theta dashed plus cos theta. And, because we said theta dashed and theta are being very close to each other, and then this becomes 2 cos theta. And so we can write down that, and 2 gets cancelled. So that is equals to D cos theta. And similarly, R plus R minus, that becomes, R square. We are multiplying. So A plus B into A minus B is A square minus B square. B square by 4 cos square theta. Okay. If D is extremely small, yeah, compared to R, if D is extremely small compared to R, then this term we can essentially neglect, and we can write down uh, R plus R minus is equals to R square. Okay. Now, if we put that in this equation, what I find that, and that is what I'm going to essentially, I'm going to remove this part. The assumption of dipole is D is extremely small. So using that assumption, what I can write down, W is equals to mu 0 P 4 pi D cos theta pi. Okay. Now, what I'm trying to do now, I'm going to, club these two terms. So let's write down, just simplify it, 4 pi PD. Let us put that together. Okay. Cos theta, cos theta. Now this PD or DP, okay, DP is a very important term. Okay, what is it? It is the pole strength multiplied by the distance between the poles. Okay, it's the pole strength multiplied by the distance between the poles, and this is what we call as magnetic moment. It's very, very important. Let us call it as M, because this we will use a lot. Okay, this is what we call magnetic moment, and this is, so we can write down this to be equals to mu 0 by 4 pi, mu 0 by 4 pi M cos theta pi. Okay. Now we have reached to something which is more reasonable, more real. Now, mu 0 by 4 pi is essentially constant, if you like, because mu 0 is the permeability at vacuum. 4 pi is it's constant, of course. Theta will depend on, with respect to the dipole, where it is located. The r is the distance, and m is the magnetic moment. So this magnetic moment is absolutely, absolutely crucial. We will see why later on. All right. So we have defined magnetic moment, which is the product between the distance between the two poles multiplied by the distance. Okay, right. Now let us say there is a magnetic field, which is directed along this direction, P. And then there is a dipole, which is not essentially oriented along the field. Here is my dipole. P plus, this is P minus. Okay, you can actually replace P plus P minus with essentially, P north, P south. It's no problem. This distance D. Suppose it is oriented with the magnetic field in which it sits, an angle theta. Okay. Now, if a dipole is actually sitting on an external magnetic field and that is not aligned with the magnetic field, what would happen to the magnetic force? What would happen to the dipole? It will try to, this field B will try to align it. Field B will try to align it align the dipole along its magnetic line, right? So, if I want to align this magnetic dipole, what I have to do? I have to essentially provide some torque, right? Let us say because of the presence of this field B, it will find a torque. So suppose the force here is F and the force is exactly equal and opposite to the side F as well. Now this F is of course will be a product of B. B is the magnetic field and P it's its pole strength. Also this is, yeah, suppose this angle, this distance will then be d sine theta. Right. So the torque experienced, let us say torque experienced by this dipole, we call that as tau, equals to F into d sine theta. Now, if we have written as Bp, right? So B. Now PD is equals to again M, right? We just derived that. So B M sine theta. So Bm sine theta is the torque. So then we can also write down that as and both of them are vectors, of course. B cross product of M and B. That is how we will define the torque experienced by this dipole. So, this torque is absolutely important. Why? We will see. The magnetic moment will also be very, very important in our further discussions. Why? We will see. Okay, so if I now look at any natural material for that, any rock or for that matter, any material, okay, we can look at it from 2 point of view. One is, of course, we can look at it as in terms of, different mineral grains present in it. Let us just, because we are earth scientists, let us just have real examples. Let us look at a rock. The rock, and then, for example, let us say this is basalt. Okay. Now, what are the major mineral components in basalts? You will find there are basically, most commonly, there are two types of minerals that we find. One is plagioclase feldspar. What is the other one? Can someone tell me? What do we find in basalt? One is plagioclase feldspar. The other one is the most common mineral. Anyone? Come on. Shikta, tell me, what is the other mineral that we find in basalt? Shikta? Come on. Anyone? Preeti, can you tell me? Pyroxene. Excellent. Excellent. What type of pyroxene? Orthopyroxene or clinopyroxene? Mostly clinopyroxene. So we will find plagioclase feldspar. They would look like laths, plagioclase laths. We identify them with lamellar twinning, sorry. And they are, and then of course we find this beautiful multicolored clinopyroxene. So we can look at this rock from its mineral point of view. They are distributed. But from when we look at it from a from the view of magnetism, okay, we can simply think that there are in this rock there are several magnetic moments. So one mineral can have more than one magnetic moment. That's no problem, but it can have one as well, and they are directed in different directions. Okay, you can think of there are magnetic moments because it's a vector. They will have a magnitude and a direction. Now, whether this particular material or this rock will be magnetic, that will depend on how these magnetic moments are aligned. If the magnetic moments are perfectly aligned, yeah, it's a magnet. Okay. If they are, 80, 70, 80% or 60% aligned, then the material is magnetic. For example, if you take a magnet, bring it close to it, it will get attracted. And if it is completely haphazardly oriented, okay, these magnetic moments are haphazardly oriented, then it is non-magnetic. So we can now have a gross classification of materials: magnet, strongly magnetic, and then non-magnetic. So these strongly magnetic material, okay, when they are exposed to a magnet for a long, long, long time, then it turns to a magnet. Okay, a strongly magnetic material where the magnetic moments are like 70-80% oriented already, and then if you keep it close to a magnet for a long, long time, that becomes a magnet. Okay? And then if they are completely haphazardly oriented, then they are non-magnetic. So this is the crude classification of materials from a magnetism point of view. But then we are going to discuss about, more scientifically how the materials are subdivided from their magnetic point of view in the next class. So I'm going to stop here the class, but let me see if you have any question. Yeah, go ahead. Anyone? No? Was it all clear? Yash and Om, Sivats, everything clear? That's very good to know. Okay, then I will stop the class here and I will see you tomorrow. And we will look at the properties, the magnetic properties of rocks in greater details. Okay? Thank you very much.